Section 5.3, Diagonalization. See the definition. An n by n square matrix A is said to be diagonalizable if there is an invertible matrix P and a diagonal matrix D such that A is P, D, P inverse. A is similar to a diagonal matrix, then we say A is diagonalizable. If A is diagonalizable, we can write in this way, and A squared, here P inverse P will be cancelled, so that P D squared P inverse. Using the same argument, we can get A to the K to be P D to the K P inverse. Also, using the same logic, we can get A inverse if A is invertible. Here, P D inverse P inverse. And also we can easily see that determinant of A is the same as the product of each determinant, but the determinant from here will be cancelled because the product is 1, so that we have determinant of D. Diagonalization enables us to compute A to the K, including inverse and determinant of A very effectively. A is given, and find a formula for A to the K, given that here P and D such that A is P, D, P inverse. Okay. Now, we already know that A to the K is the same as P, D to the K, and P inverse. Okay. So, to make a formula, to find the formula, we have to get D to the K and P inverse. Okay, what is D to the K? K power of the diagonal matrix will become like the 5 to the K, 0, and 0, and 3 to the K. Okay, that's D to the K. How about P inverse? P inverse is now, okay, for that one, the determinant is AD minus BC. So the 1 over AD minus BC minus 2 plus 1 minus 1, and change the position and change the sign so that we have here, this is 2, 1, minus 1, minus 1. That's P inverse. So we can get here A to the K equal P. That is 1, 1, minus 1, minus 2. And D to the K is 5 to the K, 0, 0, 3 to the K. And P inverse, that is 2, 1, minus 1, minus 1. So if you multiply these three matrices, then you'll get this one. You can finish it yourself. Okay, we have the diagonalization theorem. An n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors v1 to vn. In fact, once it is diagonalizable, then if and only if the columns of P are the n linearly independent eigenvectors of A, in this case, the diagonal entries of D are the corresponding eigenvalues of A. Here, more mathematically, we can write in this way. P is the collection of the linearly independent eigenvectors, and D is diagonal metric having its main diagonal eigenvalues of A. Of course, that must be the same order. So AVK is lambda K VK. So lambda 1 is the eigenvalue for along with V1. Lambda 2 is along with V2 and so on. Okay, this theorem can be proved easily using the following remark. AP is PD with D diagonal. Okay, now P is given in this way, and D is diagonal of lambda 1 to lambda n. In this definition, these are arbitrary n by n matrices. It doesn't have to be, at this moment, it doesn't have to be here eigenvectors and eigenvalues. Just we start with, in fact, two arbitrary n by n matrices, and one is the standard metric, but the other one is just diagonal metric. Now we try to get AP, then A, this P, then metric multiplication is defined in this way. A is multiplied to each the vector, so we have that. Now, how about PD? And P is the collection of vectors, n vectors, and D is the diagonal metric. So here, once you do multiplication, then here, that one is multiplied by lambda 1, and this second vector is multiplied by lambda 2. So we reach in this way. If these two are the same, then looks like here AV1 equal lambda 1 V1, and AV2 is lambda 2 V2. So we can conclude here, AP is PD with D diagonal, then the non-zero columns of P are eigenvectors of A, and the diagonal entry, the corresponding diagonal entry must be eigenvalue of A, right? Okay. By using this general the theory, you can prove this theorem quite easily. Okay. Diagonalize the following metric if possible. Okay. Yeah, to diagonalize the metric, we have to find the eigenvalues of A, and also because it's a 3-dimension, we have to find the 3 linearly independent eigenvectors of A, and we form metric P collecting eigenvectors, and also we construct D as a diagonal metric of eigenvalues. Then that's it. After here, now after finishing the construction, we can check. So AP and PD are the same, then it's good computation. Okay, let's begin with number 1. First, we have to find the eigenvalues. In order to do that, okay, from here, we try to get A minus lambda I. Okay, that is 1 minus lambda 3. And that is now minus 3, minus 5 minus lambda, and minus 3. And 3, 1 minus lambda. Now we have to find its determinant. Okay, here determinant of A minus lambda I. Okay, so we'll do cofactor expansion for the first column, and now that is 1 minus lambda, and determinant of the corresponding submatrix, which is this portion. So that is minus 5 minus lambda minus 3, and that is 3 and 1 minus lambda. Okay. Now here for that one, minus 3 times minus 1 to the, that is 2 on position, 2 plus 1, and we have to get the remainder. The remainder part is basically, okay. Now, before going there, we may manipulate a little bit to get the computation simpler. So here now, okay. Now, before writing the submatrix, and let's try to add this row to the third one, then that is 0. Now, after adding, this one is minus 2 minus lambda, right? Okay, by adding, that is again minus 2 minus lambda. So rather than that one, we can use that one, right? Okay. So we want to simplify the computation. Okay. Then for minus 3, the submatrix is these two components and these two entries. So that here, determinant of 3, minus 2 minus lambda, minus 2 minus lambda. Okay. Here, now you can easily see that it's the same quantity. And after scaling, it's 1 direction, 1 direction, so that determinant of that one must be 0. And the final one is along with the 0 for that one. So we don't have to worry about the other part. So this is 0, and this is 0, so only that one. Okay. Okay, that is same as now 1 minus lambda, and okay, determinant, that is now, okay, here with a multiplication of minus 1, we have now lambda plus 5 and lambda minus 1 and plus 9, right? Okay, so that is same as 1 minus lambda, and that is lambda squared plus 4 lambda, and minus 5 plus 9, so that is plus 4. Okay, so here there's 1 minus lambda, and here lambda plus 2 squared, right? So if we solve this characteristic equation, we reach at here lambda equal 1 and minus 2 and minus 2, right? Okay, for lambda is 1, now we have to find the eigenvectors. When lambda is 1, we start with this one. Then a minus lambda I, we subtract 1 along the diagonal. Then that is now 0, 3, 3, and minus 3 and minus 6. 1 is subtracted, so the minus 3. Now 3, 3, 0, right? Now we have to solve this matrix times x equal 0 to find the eigenvector. Now by using elementary row operations, we can do it. Okay. Here, okay, this is 0, so we'll move this one on the top after scaling. So 1, 1, 0. Rather than augmented matrix, we are using the matrix itself, because the augmented matrix is simply added only 0 column. Okay. Now, the top one, after scaling, that is 0, 1, 1. Now, we try to add here, and the result can be here. So it's 0, and that is -3 and -3. Okay, so essentially, these two are the same, so that we can eliminate this one. We reach at the reduced echelon form, 1, 1, 0, 0, 1, 1, and 0, 0, 0. Okay. Now, okay, it's not yet reduced echelon form. We have to eliminate this one. So here, okay, let's try to overwrite so that is now 0, and at the subtraction that becomes -1, right? Okay, so from this one we can say x3 is free variable, so x1 equal x3, x2 equal -x3, and now x3 is x3. So from here, eigenvectors is now along with arbitrary non-zero x3, and direction is 1, -1, and 1. Okay, so we have found one eigenvector. And how about the eigenvectors for lambda is -2. Lambda is now -2. For that one, we okay, a minus lambda I. So we have to add 2 along the diagonal to the matrix A. Okay, so here 1 is subject where that eventually we have to add 3 along the diagonal of the matrix. Now that is a 3, 3, 3, and now there is a -3. Okay, there's -3 again, -3. And 3, 3, 3. Okay, we have to solve the homogeneous system. Now, again, we are using the exactly same technique, elementary row operations, for the augmented matrix. Now, for the matrix, the roots are essentially the same, and scaling and now replacement, we reach here 1, 1, 1, and every 0, right? So that means that x2 and x3 are free variables, and from this one, now here x1 equal -x2 -x3, and x2 is same as x2, free variable. x3 is again x3. So we reach at here x, that is along with non-zero x2, direction is -1, 1, 0. Along with again non-zero x3, we have here -1, 0, 1. Okay. In fact, x2 and x3 are arbitrary, but for this vector x to be an eigenvector, they cannot be 0 simultaneously. Okay. So we have 3 linear independent eigenvectors. This one, that one, and that one. So you may here form the collecting these 3 vectors. That is this one, and this is here, and that is the last one. And of course, you have to construct a D with the same order. So start with 1 and -2, -2. So the diagonal matrix D must be given in this way. And from here, you may put this one first here, so that these two columns can be interchanged. It's okay. But anyway, you have to keep the order along with eigen values. Okay. A matrix is not always diagonalizable. Okay, let's try to diagonalize the following matrix. And for simplicity, already the characteristic polynomial is given. So here we can see that there is lambda is 1 and -2 and -2. This matrix is a simple perturbation of the matrix in the last example. Now, when lambda is 1, you can find one eigenvector. Now, let's check the two. Check if there is two eigenvectors for lambda is -2. Okay, lambda is -2. From here, a minus lambda I, that is now add 2 along diagonal, so that there is 4, 4, 3, and -4, -4, -3, and then we add here 2, so that is a 3, 3, 3. Okay. Okay. Now we have to solve this homogeneous equation. Again, we are using the elementary row operations for the matrix. After subtracting, we can eliminate this one, and this is 1, 1, 1 after scaling. Now here, so we have, okay, for example, we can write this one first, 1, 1, 1, and for that one, it's 0, 0, 0. And then for this one, now 1, 1, 1 is subtracted, so that 4, 4, 4 can be subtracted, so the 0, 0, -1. Now from here, after scaling, it becomes 1. After subtracting, it becomes 0. 1, 1, 0, 0, 0, 1, 0, 0, 0. Right? Now it's a reduced echelon form, and x2 is the single free variable, so that here x1 equal -x2. x2 is a free variable, and that means x3 equal 0. So from here, the general solution of this homogeneous equation is, along with x2 or parameter, direction is -1, 1, 0. So for lambda -2, we have only one linear independent eigenvector. From here, from lambda x1, we can have 1. You can check it quite easily. And so that we have total 2 linearly independent eigenvectors. But for this matrix to be diagonalizable, we need 3 linearly independent eigenvectors. But we have only 2. So the matrix is not diagonalizable. Okay, the section is a little bit long, so that I cut here and I save the lecture in the second part. Thank you.